Okay, so look at this deduction theorem dt. You can use it as a derived rule of inference. Modus ponens is one rule of inference. Yeah, that was the only one rule, and that was an original rule. This one I am saying you can use it as a derived rule of inference and make proofs shorter. We are going to soon see an example, yeah, how to use dt as a derived rule of inference. Okay, let me just add. We will freely use dt in formal proofs as a derived rule of inference. So a justification for a line, a reason for a line can be dt, where we are simply transferring something from left to right or right to left. However, okay, do not use it for proving little s implies little s. If you use dt there, then what does it say? Little s proves little s, which is NLA. We used that proof in the proof of dt. So please don't do that. Don't convert lemma 1 into an obvious statement. Understood? Okay. Fine. So now, if you remember, by this point in the semantic part, we had defined valuation, and we have also proven an analog of dt for semantic turnstile, yeah, double turnstile. And at that time we decided to define a theory. What was a theory? The long weekend has wiped your memory. What is a theory?
A satisfiable set.
A satisfiable set. Okay, now that is a semantic concept. Satisfiability is a semantic concept. What is its syntactic analog? Yeah, that is called consistent. So now we are going to define what is a consistent theory. So definition, but this particular definition is negative. Yeah, what is the meaning of a negative definition? We do not define what is consistent. We define what is inconsistent. And whenever it is not inconsistent, then we say it is consistent. Okay? So let us look at the definition now. So say that a subset of SL is inconsistent if for any T in SL we have a deduction of T from capital S. So you can prove anything from capital S that is inconsistent. So in particular you can prove one formula and its negation simultaneously. Yeah, we say to people, yeah, that, oh, your speech is incoherent, you are not making sense. That is an inconsistent theory. So say that S is consistent if it is not inconsistent, i.e. there is T in SL such that there is no proof of T from S. There is no deduction of T from S. Okay, so I mean, we would like to know some examples of dt of an inconsistent theory or a consistent theory. Can you give me one example of an inconsistent theory? P and negation P, yeah, where P is a propositional variable, or in general S and negation S, where S is any formula. Because I mean in the filter language, S and negation S, by conjunction they generate 0, the contradiction, and from contradiction you can prove anything. That's the idea. So we are going to simply do that. Yeah, so we will prove, we now show that S negation S is inconsistent. Okay, how can we do that? Let us start. So let T be in SL. So what do we want to show? S comma negation S proves T. T is arbitrary. Yeah, T doesn't depend on S, so we want to prove that. So we are going to start with this. The first line I will write. What can I prove from this? First, from S and negation S? S, okay, good. This is NLA. Second line. Okay, what else can I prove from this? S meet? S meet negation S. We don't use the word meet here. Do you mean conjunction? But conjunction is not part of our set of connectives right now. What are we using? Negation and implication. So we can only use, I mean from these two you obviously cannot apply any MP. Yeah, you have to add something more. What should you add?
S implies negation, S implies
L1.
S implies negation, S implies? S implies negation, S implies S. And then you will end up proving S by using MP twice. Not really helpful. You have to introduce something. So I'm just going to write this. I'm going to make it a bit more complicated. First. This one is allowed? Yes. So what is the reason? Okay, good. Fourth one. Now what can I conclude? Negation T implies negation S. And what is the reason for that? MP 2, 3. Okay. Now contraposition, law of contraposition. So S implies negation S. So negation T implies negation S implies S implies T. This is LA 4. And after that I can use MP. Okay, and then I will conclude S implies T by using MP 4, 5. And finally, I can conclude T by using MP 1, 6. Okay, so we indeed proved any T from S and negation S. Just a rewrite of this is lemma 2. Okay, so without any left hand side, I can prove that S implies negation S implies T. How do you do that? How do you prove lemma 2 from this? Look at the first line. 2 times dt. Okay? So I gave you a problem of, I gave you a solution of the tutorial problem. This is lemma 2 and here is a proof. And I can also give you a proof of lemma 3. Yes, in both these cases use dt twice. It just depends on in which order you are pulling terms in. Did anybody try to solve this problem, lemma 2 and lemma 3? Okay, so I have spoiled it for you. Okay, then there are other lemmas which they will be used later. So let me just write them here. So lemma 4 is also useful. So that is S implies negation S implies negation S. That is lemma 4. I am not going to tell you any proofs at this point because they are tutorial problems. So you should at least have some fun. So lemma 5, this is called double negation introduction. Yeah, S implies double negation S. And finally there is lemma 6. Okay, and it says that S implies negation T implies negation S implies T. Okay, these are the 3 statements where you can have fun trying to prove these things until Friday. Right, so these are the statements we are going to use. However, we are not done with the concept of consistency yet. We still need various different notions, various different results to conclude consistency or inconsistency or its characterizations. So far we have proven lemma 1, 2 and 3, 4, 5 and 6 are exercises for now, and now there will be 3 more, 7, 8 and 9, and they will be related to the notion of consistency. So let's write that. So lemma 7, okay, lemma 7 says that given S subset of SL, S is inconsistent if and only if for some little s in SL, S proves negation of S implies S. Is this intuitive? S implies S is a tautology and negation of S implies S is a contradiction. So what we are saying is a set is inconsistent if and only if it proves a specific type of contradiction. I mean, it should be any contradiction really, but in this proof we are only going to do one part. Okay, any ideas on how to do this?
No, S already proves S implies S, so we should do it.
If S is inconsistent, yes. If S is inconsistent, then S proves T for any T. So in particular, S proves negation little s implies little s. Okay, so one side is obvious. What about the other side? Other implication, that suppose you have a proof of a contradiction from capital S, how do you show that you can imply anything?
No, you can prove S implies S also, like because you can prove it from anything. So
how can you prove S implies S? I mean, I want a proof of S implies T for any T.
No, yeah, like we have negation S implies S and S implies S. So we can use the previous one and then we have everything.
Oh, negation S implies S and S implies S, and then you can prove any claim.
Yeah.
But then you have to use a cut rule. Okay, so capital S proves this, capital S proves this, and then you still need to obtain that capital S proves any consequence of this. That is called a cut rule. Yeah, so let's not go there. We want to directly conclude something. But now that we are on this page, do you think any lemma would be able to help us? Okay, let's do it in a non-linear fashion. Sorry, that was unnecessary actually. Let's do it in a slightly non-linear fashion. So, S proves negation S implies S is given. Yeah, don't write anything for now. Yeah, this is hypothesis. And we would like, yeah, what do we want? That S proves T. Okay. Then perhaps to trace back one step, maybe we used reasoning MP here. Yeah, most likely we used MP. This is not NLA, this is not LA, so we used MP. So on which one did we use MP? We only know two things. So perhaps the previous sentence was this. Okay, how do we, and then the reason was MP on appropriate lines. So enough to obtain this. Well, this really doesn't sound useful. I mean, this doesn't look useful right now. But what if we use its contrapositive? Yeah, perhaps we can use something which is useful. So, at some point, if we just have the contrapositive, which is negation T implies double negation of S implies S, then by using negation T implies double negation S implies S implies negation S implies S proves T, implies T. So this would be LA4 and then this would be appropriate MP. Okay, now we are getting closer. How do we obtain something like this? Well, this gives us the vibe of, because T is arbitrary, it gives us the vibe of LA1. Alright, so if we have LA1, then we just need this. Double negation S implies S implies negation T implies double negation S implies S. This is LA1 and then this is MP. Oh, this is MP provided we have somewhere double negation S implies S. Yeah, if we have this double negation S implies S, then using these two things I can conclude this. Sorry, using these two I can conclude this. Yeah. Now, how do I obtain this double negation S implies S? So, because of some technical glitch, we couldn't really save this part of the proof. So, let me share. So, here is the completed proof of lemma 7, the backward implication. So, let us try to look at this step 3. Yeah, I mean this step 3 we had finished, step 4 I mean. We had reached until this point that double negation S implies S we will need. Yeah, we are doing this proof backwards. Well, how do you obtain that? We know double negation elimination is one of the logical axioms. But here we don't need that, we need its converse, double negation introduction, which is precisely lemma 5. So, lemma 5, and because you want capital S to be on the left hand side, you would like it to have monotonicity as well. So, lemma 5 and monotonicity, you get this S implies double negation S implies S as the right hand side of the third line of the proof, and already S implies S, which is the left hand side of this implication, is our lemma 1, as well as use monotonicity because you wanted to increase the left hand side. And the first line is the hypothesis that negation S implies S is true. So, do you understand all these things now? So, we have completed the proof of lemma 7, and this is a really good example of how a proof can be written backwards. Writing a formal proof, as we have said on multiple occasions, is a difficult process. So, we can perhaps start from the backward, like from the last line, and then work our way backwards, as well as some way forward, and then eventually we reach the point that we wanted. Okay. So, now let us look at this lemma 8. So, our list of lemmas is not yet complete. In lemma 7, we just saw that a test for inconsistency. Now, this is another test for inconsistency, but notice that there is a slight difference here. The slight difference comes from that we are not talking about the inconsistency or consistency of a given set, but we are talking about whether we can add a single extra formula to this particular set and then decide its inconsistency. So, let us look at what is written. So, suppose capital S is a subset of SL, which means it is a set of formulas, propositional formulas, and little s is a single propositional formula. So, now S union singleton S is inconsistent if and only if negation S can be proven from capital S. Okay. See here, like there is a usual chance of confusion that what if capital S itself is inconsistent? Well, capital S is inconsistent means by monotonicity capital S union singleton small s is also inconsistent. So, capital S can prove anything, so both sides are anyway true. Yeah, so that is not really the question. Here we are trying to test the boundaries of a consistent set. So, usually whenever we use this result, we are interested in the case when capital S is consistent, but adding a new element that will explode, that will result in explosion. Yeah, like it will become inconsistent. The forward proof is quite simple. If S union singleton S is inconsistent, then you can prove anything from it. Yeah, so that's the definition of inconsistency, that S proves T for any T. So, that T happens to be negation S. So, that is our first line, it's by inconsistency. Then by using dt we can transfer this little s to the right hand side of the turnstile operator. Now, this is a perfect setup for lemma 5. So, use lemma 5 plus monotonicity because our left hand side is non-empty to get that capital S proves that S implies negation S implies negation S, and then a simple application of MP will give you the necessary result. Okay, so very sleek use of the deduction theorem as a derived rule of consequence. Okay, so for the next one, suppose we are given that negation S is a logical is a proof theoretic consequence of capital S. It can be deduced, it's a deductive consequence of capital S. Then S union singleton S, like singleton small s, has got little s as well as negation S as deductive consequences. One thanks to NLA, whereas the second one thanks to the hypothesis as well as monotonicity. Now we want to prove that capital S is inconsistent, which means given any formula T, we should be able to prove little t from capital S. And how do we introduce this unknown thing? Well, our usual idea is LA1, but we don't want to do LA1 here. Yeah, S implies T implies S is not what we are going to do. We are in fact going to use the inconsistency part like we have shown. You remember that we have shown that little s comma negation S, this two element set is inconsistent. And using that we proved that, proved lemma 2 by applying deduction theorem twice. So lemma 2 and monotonicity will give us line number 3. Okay, so S implies negation, S implies T is a deductive consequence of S union singleton S. And then you simply apply modus ponens twice and you get the result. Okay, so whenever you have both small s and negation S, then the process is really easy. There is, now these, if you understand, lemma 7 is a proof, is a test for inconsistency of a given set of formulas. This is also a test of inconsistency for S union singleton S. But now we like, so therefore both of them are necessary as well as sufficient conditions. In the next lemma, however, we are going to obtain a sufficient condition. So if there is a set from which we can prove little t as well as negation t, then S is inconsistent. The proof is not very different from what we just saw, but it is just a test of, it's just a sufficiency test, okay? And we are going to use all of these proofs later. Yeah, so you have T and negation T as hypothesis, and I just changed the letter here, like you start with U as your new formula and then you would like to prove S proves U, again use lemma 2 and monotonicity and modus ponens, that gives you the complete proof. Now after a small break we will return for looking at the proof of the soundness theorem. Important result in propositional logic is the completeness theorem. It's Gödel's completeness theorem, although Gödel proved it for predicate logic first. Propositional logic, as I already told you, it's a baby version of what can be done. Here we are going to gather ideas and then we will generalize them to the appropriate context. So completeness theorem is the connection between single turnstile and double turnstile. It says that they are exactly the same. It is also connection between satisfiability and consistency. It will say they are the same. And when you say they are same, actually there are two things. One thing is that single turnstile syntactic thing will imply the semantic thing, and conversely. One of them, whenever there are two things to prove, yeah, usually it is the case that one is obvious or much more simpler than the other. So the simpler part of this is the syntactic deduction implies semantic consequence. This part is called soundness theorem. Have you heard the phrase sound sleep? Yeah, sound sleep. Yeah, I mean, I'm peaceful. I'm not bothered by anything. So the simplest thing to expect, because see this Hilbert style deduction system, we introduced those 4 logical axiom schema. Then we came up with modus ponens, and we would like to verify that we are sound people. We haven't gone insane. Right? So in order to check that, we must prove that whatever our understanding is, whatever our semantics is, that semantics does indeed follow from our syntax. Okay? So we are going to first prove the easy part, which is the soundness theorem, and then will come the completeness theorem, which is the converse. Now by this time I have talked about these things so many times that the statement of soundness theorem is also not a surprise. So suppose S is a subset of SL and T is a particular formula. If there is a proof of T from capital S, then T is a logical consequence. This is soundness. Yeah, single turnstile implies double turnstile. Okay. What do we need to show here? What do we need to show here? Whenever there is a valuation V that makes capital S true, then the same valuation will also make small t true. So assume that there is a proof of T from S and that V is a valuation such that it is a model of S. So V is a V is something that witnesses that capital S is satisfiable, which means V of capital S is true. Just to recall things, so V of capital S is true means V of little s is true for all small s in capital S. Okay. Now we have a proof of T from capital S. What should be our way of proving this? We have a formal proof. And where will this line be? S proves T. This sequent will lie at the end. So we have to use. Are there any other ways of proving anything? Induction on line number. Okay. We will show by induction on line number that if V of LHS is true, line number of a proof of T of S implies T, S reduces T. If V of LHS is true, then V of RHS is true. Okay, tell me, what is base case 1? LA? Yeah, so line I is S proves TI LA. Then if there is a valuation V, that particular valuation V that makes the left hand side true, there is no cause and effect here. TI is a logical axiom, so TI is a tautology, so V of T is true. No cause and effect. Yeah, since TI is LA, it is a tautology. That's why that exercise, verify that all logical axioms are tautologies. It is a tautology, and hence V of Ti is true. Done. So base case 2, line I is S proves Ti NLA. Since Ti belongs to S and V of capital S is true, V of Ti is also true. Done, because it belongs to capital S and V makes everything in capital S true. Inductive case. Line I is S proves Ti MP, and well, I am going to use a different notation, JK, for a change. So J and K are smaller, right? So by induction hypothesis, if line J is S proves Tj and line K is S proves Tj implies Ti, then V of Tj is true. Yeah, because they were previous lines, so we have already concluded something about their right hand sides. So by induction hypothesis, V of Tj is true and V of Tj implies Ti is true. Okay, if V of Tj is true and Tj implies Ti is true, what can you conclude about Ti? By the definition of valuation for implication, yeah? By the definition of valuation for implication, V of Ti is also true. So we proved the inductive case. Now, what is the last line of this whole proof? Since S proves T is the last sequent in the proof or last line in the proof, by induction we are done. I mean, it looks like a long proof, but there is seriously nothing in it. Soundness is the easy part of the completeness theorem.